Thank you. Today I'd like to speak about the micronutrient needs of children 1 to 3 years of age. To understand micronutrient requirements, we have to begin by understanding the terms that are used to describe them, in particular what are called the dietary reference intakes, which are used in the United States and Canada. There are a number of terms and we'll be referring to them. The first is the estimated average requirement. This is the value or the intake needed to meet the needs of half or 50% of all individuals. More widely known is the term recommended dietary allowance, RDA. This is the recommended daily level of a nutrient needed to meet the needs of almost all in a specific age and gender group. We also have the terms adequate intake. An adequate intake is a single value that's when there's not enough data to reflect to develop an EAR RDA. It's also used to reflect the intake of breastfed babies. And then there's the tolerable upper intake level, which is the maximum long-term intake that most likely will not pose a risk for health problems for almost all healthy people in that age and gender group. It is not a target intake. So let's begin by looking at iron. So I want to begin by discussing the derivation of the iron requirements in the 1 to 3 year old toddler group. In this age group, the median requirement for iron that's absorbed into the body is 0.6 milligrams per day. The 97th percentile of requirements based on growth and losses is 1.2 milligrams per day. Most of this requirement, 60%, is what's needed for basal losses, not actually for body growth. In calculating the iron requirements, an assumption of 18% of dietary iron is assumed to be absorbed. In the United States, then, this led to an EAR, an average requirement of 3 milligrams per day, and an RDA, and some slight rounding was used, of 7 milligrams per day. The European Food Safety Authority came up with an adequate intake, which is similar to an EAR, of 5 milligrams per day, and a population reference intake, which is similar to an RDA, of 7 milligrams per day, the same value that's used in the United States and Canada. So let's now take a look at the recent data about the usual intakes of iron in small children. There are several studies in both the United States as well as those in other countries which are listed here. What they show is that intakes in the United States, Mexico, and even in Australia are approximately 7 to 10 milligrams per day, or a value that's at or above the RDA, suggesting that for the most part, intakes for toddlers were adequate. In the Philippines, however, a national survey suggested that average intakes were well below that amount, leading to some concern. When you look at these data from the United States more carefully, and then one looks at the percent below the EAR and the RDA, then overall, although virtually no one was below the EAR, only 0.4%, about a quarter of toddlers were below the RDA intake for iron. This suggests that even though average intakes are reasonably acceptable, that there remains a substantial portion of infants who have intakes that are below the RDA. Of note is that the incidence of intakes below the RDA was higher in Mexican Americans compared to non-Hispanic whites or even non-Hispanic Black populations. So what are some of the factors that affect iron absorption? There are specific enhancers of iron absorption, which include heme iron and vitamin C. And notably, there are significant inhibitors of iron absorption, which include phytates, iron-binding phenolic compounds such as tannins, and calcium. In considering iron bioavailability, although the values for the EAR and RDA are based on specific values of iron absorption fraction that was 18% on the average, it's important to note that the type of iron and the source of iron can really make a big difference in whether or not the iron is absorbed. In this study, if one looks at the 58 iron absorbed, whether or not it was ferrous fumarate or iron EDTA or ferrous sulfate made a large difference. So ferrous sulfate absorption was 7.9%, ferrous fumarate was 2.4%, and reduced iron, even with sodium EDTA, was only 1.4%. So in looking at populations, one has to consider the source of the iron as well as whether or not the other components of the diet. So to summarize some current considerations regarding iron, in industrialized countries, the intake from most small children matches the published requirements. This may be less true for non-industrialized countries, and significant shortfalls in populations, including those with anemia, persist in all parts of the world. The huge variation in iron bioavailability from dietary sources indicates that the use of one population standard for targeted iron intakes may not be useful, and vigilance is needed to identify individuals or populations with low bioavailable dietary sources who are therefore at risk for iron deficiency, despite what might seem to be an adequate total iron intake. I want to move now from iron over to zinc. In zinc, the calculation of zinc requirements is based on the method called the factorial approach. In the factorial approach, what's determined is the total amount of a nutrient such as zinc, which is required for growth, and then the amount that's in the diet, the amount that's absorbed, the amount that are lost through feces and other sources are then calculated. In the specific case of zinc for toddlers, I'm showing here the calculation, the factorial calculations is done by the European Food Safety Authority. In this case, the average requirement of 3.6 milligrams per day was determined by looking at the zinc needed for growth, which is 0.131 milligrams per day, calculating the absorption fraction, and then the losses in fecal and urine and sweat to get the 3.6 milligrams. This calculation by the European Food Safety Authority assumed 30% bioavailability of dietary zinc, which is an average bioavailability and is somewhat diet dependent. Zinc recommendations based on these type of calculations. The EAR for zinc in the United States and Canada is 2.5 milligrams per day, and the RDA is 3 milligrams per day. The European Food Safety Authority used the EAR value of 3.6, which I showed you how it was derived in the previous slide, and an RDA of 4.3 milligrams per day. Other groups, including the World Health Organization, have used a more variable calculation for EAR with a percent of bioavailability included in the calculation of the EAR. When we looked at zinc absorption to determine whether or not this EAR and these values fit with our absorption calculations, we looked at a group of 1 to 4-year-old children. And the value on which the x-axis, zinc intake, crosses the value of about 0.13 milligrams per day is approximately 4 milligrams per day. This is slightly higher than the US RDA value, but very comparable to the 3.6 milligram per day value calculated by the European Food Safety Authority, suggesting that these recommendations are reasonably consistent with the data we were able to obtain. Recent intake on the usual zinc intake from toddlers suggests that, in fact, that zinc intakes are mostly adequate in the countries that were surveyed, again, with slightly lower values seen in the Philippines. One concern that's been had is that the Food Nutrition Board upper limit for zinc was set in 2001 as 5 milligrams per day. This value may be a little on the high side, low side, because so many children did have zinc intakes well above that. The different international groups, such as the iZinc group, have reconsidered the upper limit, and they're currently based on no adverse effect level, a no L, and have concluded that the appropriate upper limit for zinc may not be 5 to 7 milligrams in 6-month or 3-year-old children, it may be 7 to 10 milligrams, making fewer infants being considered at risk for excessive intakes. So current considerations for zinc. Generally, intakes are well above recommendations for most toddlers. Zinc needs to be considered in concert with iron and other minerals, including copper, in determining fortification strategies. And dietary concerns about exceeding the upper level are likely not a reason to lower current fortification strategies. The turn now towards calcium. Shows the changes in calcium accretion in the skeleton with age. If we look at toddlers, it's about 140 to 150 milligrams per day is accreted into the skeleton. Using the same type of data, looking at calcium retention as a function of calcium intake, we plotted the curve for these in small children of this age group. We then calculated how much dietary calcium would be needed to achieve different levels of calcium retention using multiple different mathematical models. The best model for this would be the S-curve, which fit it the best. And if we looked at that retention of 140 milligrams per day, we came up with a requirement of 470 milligrams, 472 for calcium, with an RDA value for 180 milligrams of close to 700 milligrams per day. And in fact, these values then fairly well reflect the DRIs, where in the United States, the EAR for 1 to 3-year-olds is 500 milligrams per day. The RDA is 700 milligrams per day. The European Food Safety Authority has slightly lower values, but not terribly inconsistent. The good news is that in the United States and Canada, at least, most intakes are well above the EAR, and the mean is above the RDA. When we look at calcium sources from common toddler beverages, we can see that there are large variations in the amount of calcium in these different beverages, as well as the amount of intake that would be achieved by toddlers if they had an intake of about half a liter per day. This is important in counseling families. So, for example, whole cow milk, as well as fortified soy and rice and other milks, have fairly substantial amounts of calcium. Unfortified almond milk and unfortified soy milk have very low amounts. So the current considerations for calcium are that the likely average physiological need is about 300 to 400 milligrams per day. This is easily achieved with a diet that includes dairy or fortified plant or other beverages. Breastfed toddlers should have adequate solid food or other dietary sources of calcium. And one needs to be aware of this issue, especially in vegan or other more restrictive diets. The last nutrient I want to consider is vitamin D, which of course is a little different than the minerals. And I wanted to talk about initially the Cochrane systematic review, which showed that there's no overall benefit to vitamin D supplementation in those who had a normal vitamin D level. Those with a very low vitamin D level, less than 14 nanograms per ml, did have some benefit. These results do not support vitamin D supplementation to improve bone density in healthy children with normal vitamin D levels, but suggest that supplementation in deficient children may be clinically useful. When we look at rickets, we need to understand that rickets in infants and toddlers is a combination of a low intake of calcium and a low intake of vitamin D. It's not a matter of one or the other. It's also important, although many target relatively high values for vitamin D. In fact, when we looked in older children, there really is not a close relationship between the serum 25-hydroxyvitamin D level and the percentage and total amount of calcium that's absorbed in children, as long as the vitamin D level stays above about 25 to 30 nanomoles per liter, or about 12 to 14 nanograms per ml. I'm not going to go through this detail, but we've published a roadmap for action to reduce vitamin D deficiency, where we look specifically at populations. And the key piece to take home from this is that there need to be population-based surveys of the level of vitamin D in the population determines whether or not food fortification strategies or supplementation strategies, as well as changing dietary intake, can be useful. So we've published this and again regarding vitamin D on a global basis, and can give a guideline for those looking for when to fortify or when to intervene. So current considerations for vitamin D related to bone health, there's a low but definite persistence of severe vitamin D deficiency in this age group in most countries, although dietary intakes are low in many populations. Specific risk groups exist, and rickets remains a clinical problem, especially combined with low calcium intakes. Global strategies and assessments are needed to evaluate the need for fortification and supplementation. So to conclude, toddler diets are adequate for key nutrients. Specific deficiency exists with clinical consequences most important for iron. Dietary sources of bioavailability are not always fully accounted by the RDA and similar type of guidance, reflecting the need to not overgeneralize about population deficits or excesses. This age group is a difficult population to study, and more research is needed, especially in non-industrialized countries. Thank you.